spar platforms. Now, spars are actually essentially long cylindrical platforms. Now, spar essentially whenever you come across this word spar, it means long and cylindrical. No, why spar? So, that means these are essentially deep draft vessels or floaters. Now, this is where the main departure from the conventional TLPs and semi-submersibles occur, that is in the deep draft platforms. So, in some of these platforms you will find draft more than say 200 meters or 400 meters, so very deep draft. Now, why this deep draft? What is the advantage? So, here actually you will find the idea is to shallow draft, there will be lot of motions on the, because created by the waves. So, in deep draft you just nullify the motions. So, this is there to have favorable motions. Favorable motions, since the wave excitation forces do not affect the structure below the wave regime. Wave regime is near the surface. Below water surface, which is one of the main advantages. Now, disadvantage is also there, but this will be influenced by high currents. Current is going to be play havoc. So, whenever you are designing a platform, you should remember that these are the two types of forces which are going to come to the platform. Now, spars actually you will find that it will look like this. There are two types. First one is called classic and the other is truss. So, the engineering is actually based on reduction of motion and also the cost of the platform. So, there are two types, one is called a classic spar and the other is called a truss spar. Now, in the classic spar, if this is your water line, then the deck is kept above the water line. Now, the deck is more or less an open deck, truss type open deck. Here actually you will find the hull type deck is missing. So, on top of this you have your deck modules, flare, stack, etc. So, this is your deck, but we are more bothered about the structure below this deck, is not it? Now, here actually the point that is to be remembered is this type of platform will have ballast near the keel. So, this is your keel. Now, here you have solid ballast. And near the water line you have your void spaces. So, these are essentially buoyancy tanks. Now, in spars you remember that the center of buoyancy is above your center of gravity. Unlike ships, the CG is above your center of buoyancy. So, these are void spaces. Voids. So, in TLP I told you that tension leg platform has a lot of void spaces because of the buoyancy. Now, here you suspend your marine riser. So, this is the center well. Now, the marine riser in some of the spars mostly it is kept under tension by giving buoyancy tanks. So, there will be large buoyancy tanks on the marine riser. Now, these are called buoyancy cans. Good. Now, the mooring is from this end. The mooring wire is left from here. This is called steel catenary mooring. Oh, sorry, this is riser. So, this is steel catenary riser and this is another riser. So, here he is having two risers. So, this riser is having support from the side shell of the side of the well, and this is called top tension riser. Now, mooring wires are actually suspended from around, it comes from the deck. So, that is the moorings are kept taut by being reeled on windlasses. So, it will come like this and then it will go. So, this is the figure of a, so this is your mooring wire. Now, this is called at the bottom. So, this is your keel and this is called soft tank. whereas the voids can be called hard tank. So, whenever you come across spar, you will come across these words. So, hard tank, soft tank and buoyancy cans with risers. Now, here this whole cylinder is that is it is enclosed by means of the plate. Now, you can also alter the design. So, this is your water line. Now, sometimes what they do, they dispense with this part, that is instead of covering this portion, you can keep it open. So, that is called a truss spar. So, that is the only difference. So, right up to the hard tank. So, hard tank limit, this is your hard tank. So, the structure is going to be the same. Now, below this you replace it by a truss, but the soft tank is going to be there. Now, I will tell you why the soft tank is given. So, this is your part of the truss. So, you replace the cylindrical shell with this type of truss. But in between we have a diaphragm wall. Now, this is there to damp your motions, and this portion you can give a truss. So, the truss is essentially open. So, these are the two types of spar you will come across. Now, here actually the structure will be the same as this one. So, you will have your hard tank, now all these offshore structures, basic thing you should remember that the riser has to be kept under tension. So, that acts as a weight. So, you have to increase your displacement, or you have to provide sufficient buoyancy for riser support and mooring supports. So, this is somewhat your departure from the conventional ship design that we talk about. So, here you can have a flare stack, but the spars you will find that they are not very big platforms like your say semi-submersibles or TLPs or FPSOs. They are essentially smaller compliant structures. So, these structures are called compliant platforms. So, that is they move with the direction of the waves. Anyway, you have all this out here. So, this you need not bother. Now, this is your hard tank region or void space. So, essentially these type of structures have the center of buoyancy is located very high. Now, here also you have to give support to the riser. So, riser support is in the form of a buoyancy cans. Now, you have to make the structure in such a way that the whole hull of the spar actually slides on the, this is called the stem. On the stem. So, this is one top tension riser, the other riser is coming on the side. So, the structure out here is more or less the same. So, from here the thing is hollow because you have to pass the riser at the bottom. Now, here actually if you close the sides, you will have lot of entrenched water in this column that is called, that can complicate the hydrodynamics of the platform, entrained water. So, most of you have to do lot of calculations on the hydrodynamic sides. Now, if you keep this portion free, that is the motion becomes much more less because the water is able to flow, otherwise you will have entrapped water here. So, this is a diaphragm, I think this so this actually damps your heave motion, sort of damping is given. The mooring actually will come from the side. So, mooring is the mooring chain or wire is led from the top, comes down from the side, same as the previous one. So, this is your hard tank. Buoyancy cans. So, these are the two types of truss or spars which are at current they are prevalent, but again there will be lot of variations actually. Actually, the first spar came in 1960s, 63, and there is some so that was invented by the Japanese, and 1963 it was the first spar. And most of these spar platforms were used for oceanographic applications. That is, they measured the velocity of the current, etc. Mostly they are used because deep draft, So, here you just house your current dynamometer, current meters, etc. It will just gauge the current. So, that was the first use of the spar. So, after this actually the oil exploration in 1960s actually it was a telegraph installation, 1960s. So, this was a telegraph installation, telegraph in the sea, telegraph pole sort of. So, remember the Japanese were doing this in 1960s. So, this was in off Japan coast. And after this the US took up. Now, the hull diameter is I am giving you the North Sea. North Sea hull dia is 95 feet. This is on the top deck. Just to give you an idea of the size. Now this tapers to 55 feet at water plane. But the diagrams that I have shown you, that is more or less the same. The operating draft is around 357 feet. So this is just the geometry. And some spars have storage facility. Oil storage. So that means part of these hard tank, this type of spar you can have oil storage around here, okay, but don't store oil near the water plane. So that will raise your G. So that is one of the major advantage. Now here you find the spar components. Spar components you will find, the first is you have to design the deck, next is hard tank, next is the midship section, or sometimes this is called the mid section. This is a shell or truss. The last one is your soft tank. So these are the 4 structural components that make up the spar platform. Now the deck and the hard tank. The deck design. So deck design, you will find you have to make number of layers. Decks, number of layers you have to make, because you cannot spread out the deck to a large extent because of the restriction in size of the diameter of the hull. Hull diameter is a restriction. So number of layers you have to think about, and also extent of overhang. This you have to figure out from your processing facility. Now this actually will depend on 2 factors: spar designed for drilling or production. Now actually in this lecture I cannot go into, neither I am experienced in that. In your deck design, most of these platforms are based on deck design. Now deck design, actually the 2 fundamental aspects of deck design will depend on whether you are going for this drilling or production process. Your riser will actually be different. Your drilling riser is different from a production riser, and also the functions will be different. But in some platforms you can do both drilling and production. So this actually comes from field experience, which of course the teacher will not be able to give you. So the best possible knowledge that you can acquire is in the field, or in the where it is being made. You go to a shipyard, you see how spars are fabricated, installed, etc. That itself is a lot of learning. So this you remember, spar, the deck design. Now you have to start from deck design actually. Deck design, you start from how much oil you are going to recover in specified barrels of production per day or cubic feet of gas that is to be produced from the day. So, produced in a day. So, that actually influences your production processes on the deck. So, there you start laying out and then you go on layering the deck. So, that is not a very easy job. So, that comes from lot of experience and skill. So, based on that, now you decide the diameter. The next thing that is you have to decide on the hull diameter. The hull diameter and length, these are you have to find out. So, basically your spar platform, actually the size has increased with the requirement of your oil production, the size has increased, but of course, the geometry is more or less similar. Now, you will find that instead of having this one tank, this diagram, you can have number of cylinders and join it together. So, that is called another type of spar, that is called a cell spar. So, this has been I'll just show you the diagram. So, this is a, I think this has been built by Exxon or Mobil, in one of these two oil companies. So, lot of thought has been given into the hydrodynamics and the motion aspects. Now, coming to the anyway, so this discussion will be, so this is the hard tank split up into number of cells. This is another type of spar. Actually, basically you will find three types: classic, truss, cell, cellular construction. So, here the hard tank, that means the hard tank design. So, you have to fix this. So, how you are going to fix this? Now, the hull, if you take a cross section across the hard tank, you will find that your cross section looks like this. Now, inside you have a rectangular opening for passage of your riser. Now, the construction of this is little bit different from your ships. I am just giving you a sketch. So, this is called center well or center well opening for what? For marine riser. And buoyancy tanks. Now, here these are, you give support to the center well, this is a radial bulkhead. Now, here you make the framing. So, your framing will look like this. Center you have a support and you have your vertical frames. Now, in ships you will come across the longitudinal framing, but here you have framing like this. So, like this you do for all the cells. So, this is how you lay out your hard tank. Hard tank construction. So, hard tank diameter is fully dependent on the center well opening. Next, what? So, this is your hard tank layout. Now, hard tank, so this is actually your void spaces or tanks. Now, you have to find out the volume of these tanks, because you have to calculate the buoyancy. So, what you do? So, this now you can see in this diagram. So, these are actually your flats or floors, that is your bulkheads, watertight compartments. So, this is one watertight. So, like this you can divide into number of layers, say this is 1, 2, 3, 4 I have shown, but for the larger you can go up to 7. So, that means you have 7 layers of buoyancy tanks. Now, each tank will be this type of configuration. So, here actually you have to find out the buoyancy requirements, and then you calculate this width, and on top of that you do the stringer width. So, this is the hard tank layout. So, the hard tank is cylindrical in shape, that means it is a structural arrangement, structure of a hard tank. Now, remember these are not your the normal ship ballast tank. Ship ballast tank is it is integral with the hull, but here actually you can see that it is cylindrical stiffened structure. Structure wise you will have to do a cylindrical stiffened shell. Actually, this is where your structure actually departs from that of a ship. So, FEM analysis will be shell type of analysis, stiffened shell. In FEM, if you input this as stiffened shell, the ship also normally you will find the curved part is your the curvature is there. So, that is also a shell. So, FEM calculations if you do, you have to be a somewhat bit on the shell type of FEM. Now, here the another point that is to be remembered is when you are designing the structure of hard tank, you have to counter hydrostatic pressure. Similar to your TLP, because you are having void spaces. Now, in this type of offshore structure, if you have void spaces, suppose that means your say sometimes it happens in concrete gravity columns also. Any void space will tend to buckle your shell because of hydrostatic pressure. So, hydrostatic pressure has to be countered. Now, that is best I do not know whether you have studied the mechanics of a this is a curved panel, curved arch or a panel has more strength than a flat panel against buckling, is not it? So, all these hoop stress and all these things will come. So, that is why in the ROV or in the submarine you will find the shell is curved, that is because of resistance to this hydrostatic pressure. So, hydrostatic pressure is paramount in the design of these tanks, because inside you are having, that means inside you are not having ballast. If ballast water was there, then to some extent the hydrostatic pressure could have been balanced, but there is no balance in the pressure. So, that means the shell has to do the balancing work. So, shell has to be extra stiffened against hydrostatic pressure. So, hydrostatic pressure to be countered. So, your structural analysis, what is your failure modes that you have. So, the structural analysis is based on your failure modes. So, failure modes will be mostly because of failure from hydrostatic pressure. So, you have to do this of shell buckling analysis. What are the mechanics in shell buckling? So, normally I will try to give you some idea in your offshore technology class. So, shell buckling is prevalent. The other part is bending failure because of the length. So, bending and buckling is the prime failure modes of this type of structure, because of the length of the structure. So, here now you segregate into number of tanks. The other why you have the segregation of these tanks is dependent on what? Why you have made so many watertight bulkheads or watertight flats. So, tank segregation the structure is okay, we are designing the shell against buckling and this bending, but tank segregation, these has to be based on damage stability calculations. So, a naval architect has to be both thorough on the structures and damage stability for this type of platforms. Now, the other type is the mid section. Now, this is all the details of your hard tank. Now, I am coming to the mid portion, that is your mid section. Now, what is the function of this mid section? The mid section actually gives deep draft. You increase the draft. So, a lot of thought has to be given into the motions and the mechanics of the platform. So, this midship actually is dependent on draft selection. Draft selection is based on what? How do you select the draft? Ships easy to select and draft where you go through the dock or pass through the channel. There is a meeting draft. How do you select the draft? Spar draft. So, your draft selection will depend on, basically this depends on riser supports. How much riser you are going to support, and also depends on the I will tell you stability characteristics. Installation draft requirements. So, the lot of naval architecture calculations will be down there, calculating your GM actually. Now, here you will find that the installation, the reason why you have given the soft tank. Here actually, if you take the free body diagram, your free body diagram will, this is FBD, will look like this. So, spar is nothing but another type of boya. So, this is a truss spar. I am drawing the free body diagram, so the other layout will be somewhat different. Now, your wind force is going to act somewhere here. Now, waves and currents will be acting in this region on the hard tank. Current actually also, here he has written this waves current, but current will act much more downwards also in this. Then moving forces will come here. Third. Now, here is the main difference from ships. Now, the buoyancy will be acting at this region. Weight will be below the buoyancy. Weight CG. So, from this you will get a upward force, here this is acting downwards. Now, at the bottom you will find riser force. Normally these are two risers, one is called the top tension riser. And your SCR will be coming somewhere here. SCR is steel catenary riser. So, you try to find out the mechanics. Now, this type you have soft tank and hard tank coming out here. The reason I am telling you is this, because in the installation mode you will find the structure will be lying like this. So, this is in the installation mode. Now, you have to calculate your the GZ, GM, etc. in this mode. So, this is your hard tank. So, what you do if you just structure in installation mode or structure floating horizontally. Now, this is also the mode for transportation. You transport the structure horizontally on a barge like this, okay, and then you try to float it off like this. You rolled over the barge onto the sea and it floats like this. Now, you have to append this structure. Now, appending is actually done by putting solid ballast. This is why the solid ballast in soft tank comes, and this tank is to remain void. So, that is the main reason of the having the weight concentrated in the soft tank. Now, drilling yeah, another length of hard tank I have told you. So, this hull diameter I have told you, you calculate from this, and length of hard tank you write hard tank length is dependent on this thing on enclosure to buoyancy cans. So, buoyancy cans are actually totally enclosed within hard tank. So, hard tank length is, this is one parameter. The other parameter is the amount of writing arm you can get from the hard tank, your GZ. So, that is here you have to do your stability calculations. So, naval architects, if you go to offshore companies, you will be asked to do stability calculations. Stability calculation, especially your calculation of GZGM during transportation installation. So, that is one of the main reasons why naval architects are on the job. Now, most of these platforms, they are transported on the deck of offshore supply vessels. They, you do not transport it like this, because this will create havoc, truss. You can transport, say, for small distances, but not in rough seas. So, in order to be safe, you transport it on top of a offshore supply vessel, and there you have to follow strictly your ABS requirements. So, wherever you go to shipyards of these contracting firms, you look up ABS mobile offshore drilling rig, MODU transport rules. So, all these manuals you will find in the offshore companies. They have all these API codes, ABS, DNV and all this. So, when you go to the companies, you will have to rake up all these rules. So, this is, but you have to do the stability calculations during installation and transportation. It is a major part of calculations for naval architects. The other part that will come during the how do you transport a semi-submersible or a TLP transport. So, towage, stability during tow is a very important consideration. But here you have to find out vessel motions. So, these are some of the challenging areas you will come across in offshore transport, because offshore you will find the structures are literally very large. The spar, actually you will find the depth of the spar is around say 400 feet. So, that is more than 100 meters, 100, 200 is about huge. Our problem is transportation of very large structures.